So a lot of people have been requesting that I make this very specific video for a while, which is my thoughts around transformers and why I am not big on transformers. I'm kind of very bearish on transformers overall. So I created this, which is the anti-corporate AI pitch deck. Wasting your money on AI-based NFTs would be more profitable than transformers. So starting off, transformers are not all you need. My first two arguments are going to come from this particular research paper on limitations of the transformer architecture, which was published on February 13th, 2024. All of my arguments are going to be with regards towards the mathematics of the architecture. All of my problems with it, everything I think about it, is with regards towards math and the theory behind that, and just how physics works and math works. So hallucinations are mathematically baked in, theorem 1, and they break this down. So the proof that they break down and they essentially create, it relies on complexity theory, which is a subfield of complexity theory in which it relies on communication complexity, which is a subfield of complexity theory in which one measures the number of bits that need to be exchanged between distributed computational agents possessing different parts of the input in order for one of them to obtain the result of the computation. The agents are assumed to have unbounded computational capabilities and to be restricted only in terms of their communication. One important classical result in communication complexity is the communication difficulty of the set disjointness problem. If Bob and Alice are each given a vector of n bits and they want to compute the Boolean inner product of these vectors, that is, to tell if there's an index I such that the ith bit of both Bob and Alice is I is a 1, then they must communicate in n bits. In fact, the result is this results in the impossibility proofs. So essentially what happens within this is that what we see within this equation is that it's in order to solve a problem, like the solution space of the problem, however, like the larger the solution space of the problem it is, the more the larger it is in space to search through. So the larger mathematically complexity-wise it is for the transformer to search through in the space, and it can only perform in this instance linear searches. It can't it can't do calculations to drop these equations unless we build those equations in to make it more less linear, and then what we're doing is we're introducing loss in that instance to overcome that. So we could introduce loss and that would solve it, but then you're making it lossy, right? And you don't solve the hallucination problem overall. Problem number 2, the chain of thought required for a transformer to solve a problem scales. So this is their theorem 2, where essentially the bottom line that they break down within this particular proof is they again utilize communication theory and communication complexity, and they call pointer chasing, which is essentially where you have two positive integers chasing the problem. So in this instance, Alice knows a function and Bob knows another function, and the pointers recursively defined as the function, but they essentially run into complications and errors with each other, right? And then so within this particular equation overall, what happens is that the more complex a situation is, the more chain of thought is required. And there's not only that, but the inverse of this equation is true, which is also important too, right? So if no matter if the problem is a simple problem or a hard problem, it requires a massive amount of a chain of thought just to get to the solution. And it requires a minimum amount of chain of thought just to get to the solution, or you don't get to it. And that's just how the attention mechanism works, right? This is flaws with the math of the attention mechanism overall. Furthermore, this scaling problem leads to increasing computational complexity to solve even simple problems. So breaking this down even further, theorem 2 establishes a lower bound of the number of chain of thought steps required for a transformer layer to correctly solve iterated function composition problems, showing that it requires at least the equation depending on the number of parameters for the number of steps. The proof leverages a reduction from the pointer chasing problem in communication complexity, where two parties, Alice and Bob, sequentially follow function mappings to determine a final output after a series of rounds. Known results in communication complexity establish that solving pointer chasing requires significant information exchange. by demonstrating that a transformer layer solving k-iterated function composition would enable an efficient communication protocol for pointer chasing, the theorem links the computational demands of the transformers to fundamental lower bounds in communication complexity, reinforcing the necessity for essentially scaling within this instance and scaling problems. Next, the biggest problem within this is the quadratic scaling of the attention mechanism itself. So going into the attention mechanism and the attention layer, the quadratic scaling of attention in transformers becomes problematic because the number of computations grows exponentially with the input size. Specifically, if an input sequence has n tokens, the self-attention mechanism needs to compare each token with every other token, leading to a exploding equation. This equation, it's quadratically explosion, right? So this means that the doubling the input leads to quadruples the computational and memory requirements, making it infeasible for long sequences. As n increases, the model quickly runs into hardware limits, requiring enormous memory and processing power, which restricts scalability and efficiency, particularly for large-scale applications. And there's no way around this equation, right? The bigger the model goes, the more your quadratic scaling complexity is, which means that the model is more and more inefficient the more that you scale. And we know this. we know this problem already exists, and then that inefficiency scales to a point where it's just ridiculous. Furthermore, what this means mathematically overall, and this is like the big part of this that people just like they flat out ignore, right? Either ignore or don't understand. The problems in the attention mechanism lead to just flat out brute force computations. The transformer architecture is mathematically inefficient in training because it treats every token in its sequence equally, requiring this quadratically expanding comparisons for self-attention, leading to a massive computational overhead. Unlike models that learn incrementally or hierarchically, transformers rely on a brute force pattern matching across huge data sets, needing billions of tokens to generalize well. This inefficiency arises because the model doesn't inherently understand structure. It learns by memorizing vast amounts of correlations, making training expensive and requiring enormous amounts of data, energy, and hardware to achieve meaningful results. This is built into Transformers architecture itself. I understand why the entrepreneurs went all in on this, right? Because it has the elements that you want within it. It has elements that you can capture. Training is expensive. It requires enormous amounts of data and energy, and the hardware to achieve it is to achieve meaningful results is expensive. All of these elements are capturable, right? The problem is that there's in a free market society where you have competing architectures, this architecture gets whooped by architectures that don't have these same problems. And it turns out, oh, there's a whole bunch of them. And then like betting on this one because it was the first one that worked is actually in this situation. So tokenization, and another problem, the last problem here, specifically with transformers, is that tokenization itself is extremely lossy, and then tokenization itself is built into transformers itself. So tokenization is extremely lossy because it breaks down text into fixed units or tokens, stripping away important contextual, structural, and semantic nuances. In traditional transformers, this means that the model processes fragmented representations of words or subwords, losing information about meaning, relationships, and intent. This forces the model to relearn context through vast amounts of training data, making it inefficient and prone to errors, especially in handling ambiguous, rare, or out of vocabulary words. As a result, transformers struggle with deeper reasoning, maintaining coherence over long sequences, and adapting flexibility to new concepts. I try to stress this particular concept here over and over again in my videos, right? Like, to me, it is amazing that the LLM architecture and the transformer architecture actually works. Essentially, what you're doing is you're giving it an input, right? You get so here's an input. Here's something. Here's a question that I have. Here's a gun. Point it to your head. Pull the trigger, and then once you do that, then what's the result? Okay, and then you spit it out. That's what this does. Like, I mean, that's literally what is going on here every single time that this model is predicting a sequence, a token in the sequence. It's just obliterating all of its prior knowledge and then poofing a prediction out of that. It's the secondary problem with this is that this forces the model to relearn context through vast amounts of training data. This is the part that people don't understand. And again, I highlight this over and over again on my channel. The model is not actually learning your data set. It's learning the shape of your data set, right? learning, it's translating your data set into its own language, into LLM, we'll call it LLM language, and then LLM language is what the model is actually learning. So like it's like 2 steps removed. Like the fact that it's actually doing that it learns to do that, and then it does it is amazing. Like all of that is amazing in and of itself. Like that should be award worthy that that's actually going on. But so with Transformers architecture, you're putting in all of these barriers, and then it just overcomes them, right? Like, and then people like knock this as a bad thing against the architecture. Like I'm like, if you went outside and I'm like billy clubbing you in the knee every single time, and then you're like, oh, that guy can't walk right. Like I mean, like you're billy clubbing the guy in the knee every single time he goes outside. Like I mean, yeah, and then you're criticizing him for not being able to walk right. Like I mean, that's what is going on with Transformer architecture overall. So why does all of this actually work then if all of this works against it? And then the answer to that is very simple, right? I've mentioned it a few times throughout this video, which is complexity theory. Complexity theory analyzes the efficiency of algorithms by studying how their resource requirements, time and computational steps, and space, memory used, grow relative to the size of the input. It categorizes problems into complexity classes such as P, problems solvable in polynomial time, and NP, problems whose solutions can be verified in polynomial time but may not be solvable efficiently. A central question in complexity theory is whether P equals NP. This is a massive problem, the number one question within complexity theory. Does P equal NP? Meaning whether problems that are easy to verify are also easy to solve. The process involves defining formal problems of computation, like Turing machines, analyzing the number of steps an algorithm takes in the worst, average, and best cases, and proving whether a problem can be solved efficiently or if it becomes infeasible as input size grows. This field is essential for optimizing algorithms, cryptography, and understanding the theoretical limits of computation. Essentially, what this means is that there's several different ways to solve problems. Building a computer isn't necessarily about building the best computer or the necessarily. It's not like I need particle A plus particle C exactly plus like this exact mixture. It's not chemistry, right? It's more alchemy, meaning that I just need to take like a bunch of complex stuff and I just throw it together in a big soup and then something's going to happen. Yeah, I'm going to get some complexity out of that. Just because if I just throw enough complexity in there, complexity is going to emerge as a result. Like, just pile it on. Like, it will happen mathematically if you throw enough complexity in there. And that's kind of how this all works overall, right? And so that's what you're doing. And then so, like, sure, it works, but there's other ways to do it, right? We could throw less garbage on the pile and get the same result. So what is examples of this less garbage? I'll just like I don't support like any one of these in particular. These are just like kind of the leading examples of alternatives to transformers that exist, right? And then so with this, I'm going to highlight for you. These are like big research areas, and each one of these is a research area in and of itself, just like transformers, right? And then I don't know all of the answers to any of these questions. Like, are any of these like fully efficient? Like, will any of these be the one that takes out transformers? I don't have the crystal ball. Like, within all of this, we're dealing with mathematics and mathematical complexity, and again, complexity theory, in which you are dealing with building up big piles of garbage, and then some piles of garbage operate better than other piles of garbage, and some piles of garbage can be smaller than other piles of garbage. And then what exactly makes up the garbage, etc. These are all the open questions. So, like with that said, let me dive into the alternative architectures. RWKV. The RWKV model is a type of artificial intelligence that combines the strengths of 2 different approaches. It's a combination of transformers and recurrent neural networks, or RNNs. Transformers are good at understanding complex information, but can be slow and require a lot of memory, especially with long text. RNNs, on the other hand, handle long text more efficiently, but sometimes struggle with understanding complex information. RWKV aims to offer the best of both worlds by being efficient like RNNs and capable like transformers. This means it can process long pieces of text quickly and with less memory, while still understanding the content well. RWKV models, if you use them in a real world situation, like they're great until the attention window fills, and then once that happens, the model falls off a cliff. And I don't know, that's the problem with these models. And that's my problem. I'll give my 2 cents with RWKV. Why hasn't RWKV taken over transformers? Because if you use it for, let's say, 100,000 tokens, or whatever that context window is, it's amazing. It's wow, this is talking to the most advanced human that I've ever talked to, right? And then it's there's no question that the model is actually internalizing stuff. This is amazing. And then you get to token 100,001, and it's oh, I don't know anything. It's wow, what happened? Okay, there's interesting, right? Maybe the model's not actually learning. Maybe I don't know, what there's something weird that goes on with RWKV. So that's my RWKV. That's my assessment in a nutshell. Large concept models. Jan LeCun, a prominent figure in artificial intelligence, has introduced the concept of large concept models, or LCMs. Unlike traditional AI systems that process information word by word, LCMs aim to understand and work with broader ideas or concepts. This approach allows the AI to grasp the overall meaning of a sentence or image, making it more adept at tasks like summarizing information or understanding context. By focusing on these higher level concepts, LCMs strive to process information in a way that's more aligned with human thinking, potentially leading to more intuitive and effective AI interactions. With LCM models overall, I would say that they're the most mathematically sound out of all of the competing architectures within this. It's the one that I'm assuming is thought about the most and the longest, considering who is the one that is the creator of these models. And there's some very unique architecture that I like within these models overall. These models are fascinating to me. Though one thing, overall, LCM models are great and fantastic. I'll leave it there for this video. Next, evolutionary algorithms. Evolutionary algorithms are computer programs inspired by natural evolution, utilizing mechanisms like selection, crossover, and mutation to solve problems. When applied to neural networks, systems designed to mimic the human brain, these algorithms help optimize the network's structure and parameters. This process, known as neural evolution, enables the system to learn and adapt more effectively, enhancing its ability to make decisions and solve complex problems. People are just now starting to dive more and more into this research area, and you can combine evolutionary algorithms with neural networks. There's a few companies that are on the bleeding edge that's exactly what their field of interest is, and where they are. And then I can say very specifically, if you think the most prominent people throughout the history of AI are backing evolutionary algorithms. If you look at all of the players involved, you just a broad survey, who's doing what technology, what company is, what small company here in this area is doing A compared to B. The biggest consensus is evolutionary algorithms. So if the smartest people in the room and the longest people in the room are looking at these, and longest lasting people in the room are looking at this, I would highlight this, evolutionary algorithms. Hyperdimensional computing. Hyperdimensional computing is an innovative approach to processing information that draws inspiration from how the human brain operates. Instead of using traditional binary code, HDC represents data as a high-dimensional vectors, often comprising thousands of components. This method allows for the encoding and manipulation of complex information in a manner that is both efficient and robust. One of the key advantages of HDC is its resilience to errors, even if its parts of the data become corrupted. The overall information can still be accurately retrieved. Additionally, HDC systems can perform computations directly where the data is stored, reducing delays associated with data transfer. This brain-inspired computing paradigm holds promise for advancing artificial intelligence by enabling machines to process and understand information more like humans do. Up front, very specifically, I do not have direct financial ties to any area of AI advancement in any of these areas except for HDC. I have very direct financial ties to HDC overall, and then so I would be financially biased towards this particular technology overall, and I can't really go into depth into this technology overall for those reasons. So, but I'd be remiss to leave this off of a list like this. So hyperdimensional computing. And then the last one here I want to mention is Transformer Squared. So Sakana AI has introduced Transformer Squared, which is an advanced artificial intelligence model designed to adapt its behavior in real time to handle various tasks. Traditional AI models often require extensive retraining to learn new tasks, but Transformer Squared can adjust itself on the fly, much like how humans can switch between different activities seamlessly. This adaptability allows the model to efficiently perform tasks such as math, coding, reasoning, and visual understanding without prior specific training for each. By dynamically modifying its internal settings, Transformer Square represents a significant step towards more flexible and efficient AI systems that can learn and respond to new challenges as they arise. The number one thing I like about Transformer Square overall is that it's created by two of the original authors of Attention Is All You Need. And then so at the top of this video, I mentioned here's like all of the flaws with Transformers, right? And then if I'm able to do that, like imagine the creators of Transformers, right? Like how much like sleep do they lose at night? Like I was a noob when I invented Transformers, and then like here's what I would have changed, and here's what I would have modified, right? And then so that's exactly what Transformer Square is. And then like that's why like and then you read the research paper and what the model is, and it's like to me it reads exactly like that. Like if I were in their shoes, it's like all of the problems I point out at the top of this video with Transformer, they address very specifically with Transformer Square. So there are alternative architectures that exist and within this, right? But like the bottom line is that these are alternative architectures. Like these are not Transformers. These are not these are not OpenAI's moat. These are not Starlink, whatever, like Star Wars, whatever. Like it's not whatever is already invested in AI. These are if one of these takes off, those people are losing out on their investments. And then so I think like you see a lot of that within AI, like overall, right? Like that dictates so much of this conversation right now that it's not even funny. Like so many people are just so financially tied to all of this working out that it's like information like this. I'm going to get a few downvotes just because of this overall. I understand that overall, right? But so if you like this type of content and this messaging overall, then like and subscribe. Thank you very much.